Welcome back to the next video covering Unit 1, and in this video we're going to look at numbers and quantities. Now if you've seen the previous videos, then you should be familiar with what binary, denary and hexadecimal. So yeah, make sure you're familiar with those right before moving on to this. So this video, well, we're going to look at I guess two different types of numbers, right? The first being integers or whole numbers, right? Then there's going to be, well, reals or floats, and these are just decimal numbers. Right, then we're going to look at our signed and unsigned. Now, I think we've mentioned this, and well, this video we're just going to touch on it super quickly. But unsigned, well, this means positive only, alright, since there's no sign. Then if we look at signed, well, this means positive or negative, alright, since we do have the sign. Right, then we're going to look at the different prefixes, so I guess, well, kilo, mega, giga, and tera. Right, also these four additional ones. So I think these, right, people should be familiar with probably. So of course, right, kilo, that means 1,000, right, mega means 1,000,000, giga is 1,000,000,000, right, tera is 1,000,000,000,000. But this one, well, Kibi, Mebi, Gibi, and Tebi, right, yeah, maybe people are unfamiliar with these. Yeah, they might be new. Right, then we'll just look at how to convert between them. So first then, we want to look at the types of number in a computer, and well, as mentioned, there's two different types of number. Yeah, and of course, right, I mean, yeah, one of these is going to be, what, integers, the other one is going to be, well, reals, alright, also called floats. So the reason for these different data types is due to efficiency, because basically we just want to store as much relevant information in as few bits as possible. And of course, when we say efficiency, well, that's talking about speed, right, and also memory efficiency. So obviously, yeah, I guess, you know, using as little memory as possible. So let's say, for example, well, if we have a variable called number of students, then there's no point, for example, using a variable that can store, like, you know, billions of different students. Because, I mean, what realistically, what maybe a class has like 30 students. I mean, if it's a university, what maybe you have like 200 or something. So in this case, yeah, of course, well, we can choose a relatively small variable size. Right, and we're also going to want to think, well, this should be an integer. And of course, again, the two choices, well, either we can choose an integer, which is a whole number, right, or we can choose, well, a real or a float, yeah, which is going to be a decimal number. And of course, well, students, you know, we can't have like 1.5 students, right? We can only have, yeah, 1, 2, 3, right? Yeah, I guess only integer values. And yeah, as mentioned, well, it's probably going to be relatively small. Now, in pseudocode, you know, yeah, I guess we just have, you know, just an integer variable type. So, I mean, basically, well, that's going to be 64 bits. So in pseudocode, what we can represent, so if we think the range of this, well, okay. Yeah, I suppose when you, well, pseudocode, right, we don't have signed or unsigned. But okay, if we were using unsigned only, right, then what the smallest integer we could represent would be 0. And then if you remember from the previous videos, the biggest integer we could represent, well, with 64 bits, is going to be, what, 2 to the power of 64 minus 1. So yeah, I mean, whatever number that's going to be. Now, if we were doing, and of course, right, okay, yeah, let's say in pseudocode, right, integers can also be negative. So in that case, right, the smallest value is going to be, what, minus 2 to the n minus 1, like that. And here, what, n is, okay, well, yeah, n is going to be 64. So effectively, what, yeah, minus, right, 2 to the power of 63. And then we say, well, 2. And then right here it's going to be, what, 2 to the n minus 1 minus 1. Right, that's going to be our range. Now, again, like mentioned, right, in pseudocode, we don't have to worry about specifying the size of the integer. Yeah, sorry, specifying. Likewise, in other languages like Python, right, we also don't have to. If we look at languages like, let's say, well, C++, right, also things like Java, then here, I mean, yeah, here we can. So for example, C++, well, we can have like an 8-bit, yeah, let's say like an 8-bit signed integer, right, or an 8-bit unsigned integer. And the reason for that is, of course, well, I mean, it's going to be more efficient, right, we're going to use less space. So if we only need 200 students, then, you know, there's no point using 64 bits, because, yeah, that's going to give us like way too many. You know, in that case, well, let's say we just want, I don't know, like 0 to 255, right, and well, 0 to 255 we can represent just using 8 bits. Yeah, if it's unsigned, right, so positive only. Alright, so I think, well, this we just mentioned, right, integer, just a whole number, right, 3 is an integer, 3.1 isn't. And as mentioned, integers come in two forms, right? So unsigned, which means, well, positive only, and then signed, well, positive or negative. So when we say sign, well, this refers to the actual, yeah, I guess the sign, right? The plus or minus sign. That's why, of course, if it's unsigned, well, unsigned means, what, we have no sign, right? Therefore, if you think of a number, well, if you have a number with no sign, I mean, by default, you're kind of like assuming that's positive. right? So yeah, that's why it's called unsigned. Right, well, signed, yeah, if we do specify a sign, right, of course, then we say, well, either +3, right, or -3, right, yeah, therefore, of course, it can be both. Yeah, it can be, well, positive or negative. Right, however, the thing to note is that, I mean, I guess, you know, the computer is not actually storing, like, the plus sign, right? The computer is not storing, you know, the minus sign. The way this is actually represented, and we'll see this in a future lesson, right, not this video, but we say the most significant bit in a signed integer is negative. And if you remember, the most significant bit, well, let's just do an example. So what the most significant bit is going to be the leftmost bit, right? The least significant bit is going to be the rightmost bit. And of course, well, the reason it's called most significant is because what it is, yeah, has, you know, the biggest value, right? The least significant, well, because it has the smallest value, right? It's on the right. So in this case, well, here, I mean, here this is just going to represent 7, since we see, well, the most significant bit is well, 0, right? Which of course, yeah, that means positive. Now, if and again, right, this is going to be a future video. But let's just say this, for example, or yeah, I don't know, maybe let's do a 1 here. Now, what we're saying is, well, rather than representing 8, right, and well, this is using something called 2's complement, yeah, or equivalently, right, just saying, you know, using signed, right, rather than this representing 8, okay, right, now it's going to represent -8. So here we're saying, well, we've got -8, right, well, this one is a 4, this one is a 2, this one is a 1. So here we've got, well, -8 and then, well, +2, right, so that's going to be, well, -6. And again, you know, don't worry if you don't understand that, since, well, we're going to cover it in a later video. Right, then, if we look at fractions, well, I mean, in maths, fractions are common, but yeah, in computers, I mean, fractions are not really used. I mean, at least not natively, you know, by the processor, or yeah, they're generally not supported, right, in most programming languages. I mean, certainly not part of, you know, the standard library. Yeah, I guess it's going to be possible to get, you know, third-party libraries that can represent fractions, but yeah, I mean, generally, right, not built into the language usually. Alright, so well, instead, yeah, computers are just going to use, well, reals or floats. I mean, basically just decimals in maths, right, i.e., you know, 0.5. Now, again, for pseudocode, well, you're going to call it a real. I mean, a float, we'll actually see this is kind of a specific type of real number. Because if we think, well, okay, so like a real number, now in maths, well, a real just means anything that's not an integer, right? So yeah, anything that has, you know, a sort of non-zero decimal place. Now, real, there's actually going to be 2 types. Well, one is called floating point, right? One is called fixed point. Now, yeah, for AS, you don't need to know this, right? That's going to be A2. So I think for AS, right, I mean, just call it real. Okay, yeah, don't really worry about float or fixed. Although, yeah, if you do see float, okay, I mean, just think of it as being kind of, yeah, I guess yeah, kind of analogous, right, or the same as being a real. And yeah, I mean, as mentioned, right, although fractions are not supported natively by the processor, I mean, it would be possible to create an implementation of fractions. And the way you would do that is, well, I don't know, okay, let's say you have some fraction, like 2/3, I don't know, plus, yeah, like 1/4 or something. Well, I mean, you would actually have to kind of hand code the logic for how you would do this addition. And to be honest, I mean, I've actually completely forgot fractions, you know, it's been 10 years since I've done it. But, I mean, yeah, well, I guess, you know, yeah, of course, well, whatever logic you need to do this, I mean, yeah, you would just need to code that same logic, right, into your, you know, fraction library. Right, so if we look at decimals, well, right, decimals are called reals or floats, and well, again, float is short for floating point. Yeah, just some examples. And I suppose, I mean, this one, what that's going to be pi. This one, I think, is it the charge of an electron? Or yeah, I don't know, maybe the mass of an electron, or something like that. Right, for AS, so okay, yeah, so for AS, you're not required how these to know how they're represented in binary. However, you do need to know the name of the data type, which is real. And yeah, this is going to be used, well, in pseudocode for paper 2, right, and also for SQL, right, databases in paper 1. And I mean, in databases, well, either you can call it real, okay, or you can also call it a float as well. Yeah, both of those are acceptable. Right, then if we look at, well, scientific or standard notation, and again, I mean, hopefully from maths or physics, right, or yeah, also chemistry, you know, probably you know that we can represent numbers, well, like, well, 300 million, right, as, well, 3 times 10 to the power of 8. And of course, like, kind of what that's saying is it's saying, well, 3, right, and then multiplied by, what, 10 to the power of 8. So 10 to the power of 8, well, that's going to be a 1 with 8 zeros. Okay, yes, yeah, so like this. And then of course, well, if we do this calculation, you know, 3 times 100 million, well, yeah, that's what gives us, you know, our 300 million, right? Yeah, that's just how that works. And yeah, I mean, this is why they're called floating points, since what we're saying is, well, the decimal point, the decimal point is kind of moving back and forwards. Like for example, if we just have this, well, right here, the decimal point is here, right? It's kind of like saying, well, 300 million, you know, 0.0. But in this case, I mean, this is like saying, well, I mean, 3.0, right, multiplied by, you know, 10 to the power of 8. So what we're saying is, of course, well, I mean, to go from this one, right, to this 300 million, well, this decimal point has to kind of jump, what, 8 places to the left. Yeah, so that's why it's floating, right, since, well, the decimal point is moving. And again, I mean, this is going to be the same in binary, but I guess rather than calling it a decimal point, right, you can just call it the binary point. And again, yeah, that can float left or right, okay, depending on, well, the magnitude, right, so yeah, just the size, right, or the absolute value of the number. Right, so yeah, as mentioned, well, floats also support non-integer numbers, and that's because, well, for example, 16 times 10 to the minus 20, right, can also be written as, well, 1.6, right, yeah, times 10 to the minus 19. And of course, I mean, if you did this, I mean, what this is also going to be a, yeah, that's also going to be a non-integer, because what it's going to be, what, like 0.000, and then obviously what there's going to be, yeah, 16 at the end. Right, so if we look at quantities, well, rather than saying, right, 10,000 meters, we could also, of course, just say 10 km, right, or, yeah, well, yeah, 10 km. So, I mean, let's think then, what does the K mean? Okay, so hopefully you know, well, the K is going to mean kilo, alright, so, yeah, well, of course, right, 10 kilometers, and, well, kilo is going to mean 1,000. Right, now, if we look at some of the others, now, honestly, like, a lot of these you don't need to know, right, the only ones you need to know are going to be the multiples of 3. So here we say, well, kilo is 1,000, right, mega, well, that's 6, right, so that's 1 million. Alright, giga, well, 9, right, 1 billion, and tera, 12, so trillion. Yeah, I mean, these others, like, I mean, yeah, this one, right, this one, yeah, just, you know, ignore those. I mean, yeah, likewise, you know, peta and exa, I mean, they're kind of too big, right, you don't really have to think about that. Because, I mean, let's say if you think about, I don't know, maybe your hard drive or your SSD, well, probably, I mean, I don't know, like, maybe it's 512 gigabytes. But I think these days, often, you know, when you buy a new computer, well, it's going to be a 1 terabyte hard drive, or, you know, 1 terabyte SSD, yeah, maybe 2 terabytes. I mean, if you get some expensive, you know, I don't know, like gaming computer or something, right, maybe even 4 terabytes. So yeah, I mean, and that's why, you know, terabytes is generally the maximum you need to know. Now, if you start talking about, I don't know, let's say the amount of data that, you know, YouTube stores, right, I think that's probably going to be either, well, peta, right, maybe even exabytes. Likewise, if you start talking about, I don't know, maybe the amount of traffic sent over the internet in 1 year, right, I think the amount of traffic sent on the internet, right, that's also going to be exabytes. But again, you know, for day-to-day use, right, yeah, you're not really going to use those. Likewise, the ones that are less than 0, I mean, I guess in, well, of course, in like physics, maths, I mean, yeah, of course, well, you know, centimeters, right, like millimeters, milliliters. I mean, like for computer science, I mean, sometimes you're going to use micro because, well, you'll be doing like microseconds or also nanoseconds, right? Yeah, timing how long something takes to execute. But I mean, yeah, for the exam, right, you don't really have to worry about those. So yeah, I guess, well, for the exam, right, the only ones you need to know, right, it's just going to be these. And again, well, tera, that's the prefix T, right, giga, G, right, mega, M, yeah, well, right, kilo, K. And again, we said, what, 10 to the power of 12, 10 to the power of 9, 10 to the power of 6, right, 10 to the power of 3. And of course, what, going from, well, 1 trillion, right, and then, yeah, down to 1,000. And yes, sometimes the K is written in lowercase, and I guess, like, I think basically, well, that's just because, I mean, people have been written, well, people have been writing KM, you know, in lowercase for like hundreds of years. So yeah, even though technically it should be uppercase, yeah, of course, sometimes you will see this in lowercase. So you might see something, I don't know, like say 4, for example, KB, right, that's a small k. But yeah, of course, you know, you can also write that as well, big K, right, both of those are going to be equivalent. Right, so here, well, let's think then, how many bytes are in 1 kilobyte, 1 megabyte, 1 gigabyte, and 1 terabyte? And I mean, as long as you know, of course, what these prefixes mean, right, then hopefully you can see what 1,000, again, up to 1 trillion. Right, then let's think, well, how many bits are in 1 megabyte? So, I mean, first, if you think, well, yeah, I guess, well, how many bits are in a byte? So, of course, well, this is going to be, yeah, I guess what we need to, well, multiply by 8. Because we say, what, yeah, 8 bits are in 1 byte. Now here we can think, well, mega is going to be 1 million. So let's just do this. Right, it's going to be 1 million. Okay, yeah, right, 1 million. All right, and then well, just multiply by 8 because again we say what 8 bits are in 1 byte. Yes, that should just give us 8 million. Right, then the next one, how many bytes are in 1 gigabit? So right here then, well, let's think giga. Right, giga is going to be what, 10 to the power of 9. Yeah, right, 10 to the power of 9, which is a billion. And then in this case, so I guess, yeah, okay, right, this is going to be a billion bits. But then since we want to convert to bytes, well, we then need to divide that by 8. So yeah, this is going to be what, 1 billion, right, divided by 8. And if we do that, right, that should give us, yeah, 125 million. Right, and then here, yeah, so we also have to remember that, well, a lowercase b equals bits, right, then uppercase b is going to be bytes. So for example, MB, right, well, so I guess, yeah, like M capital B, right, that's going to be megabytes, right, while M lowercase b, right, that's going to be megabits. So, I mean, often, yeah, people get confused about this, or to be honest, like, most people don't even know there's a difference, you know, they just, I mean, yeah, probably people don't even notice that, you know, sometimes they use big B, sometimes they use small b. And I guess when I say people, I just mean, you know, regular people. You know, if you're like, yeah, I guess, I know, yeah, super into, you know, computer science, technology, right, I mean, yeah, maybe you realise there's a difference. But, you know, just like a normal person, right, when they buy their, you know, monthly phone package, I mean, yeah, they're not really going to notice there's a difference between these. And so let's think, right, when you buy the phone package, then what unit was likely used and why? And I mean, this question is kind of more to do with, let's say, like marketing or, yes, like psychology, really. So yeah, most likely they're going to use MB since, well, basically, I mean, yeah, the number is going to be bigger, right? So there, of course, it's going to feel more, yeah, I know, like more desirable, you know, like the people are going to feel like they're getting more data effectively. So let's imagine that company A offers 20 gigabits of data at a speed of, well, 2 megabits per second. Now imagine company B offers what, 3 gigabytes, right, at 0.5 megabytes per second. So which company would the average person choose? And of course, if you think about this, well, I mean, the average person is just going to choose what they're going to see 20 versus 3, right? They're going to see what, 2 versus 0.5. So of course they're going to choose A, right? Because, well, yeah, they're going to assume that's bigger. Right, but then if we actually think, so yeah, I mean, well, which company actually offers a better deal? So I mean, here we can just convert this, and remember that we said, well, to go from bytes to bits, we're just going to multiply by 8, right? So 3 times 8, well, that's going to be 24. So this will be what, 24 gigabits. Right, then of course, well, 0.5 megabytes. Right, let's multiply that by 8. Right, that's going to be 4. And yeah, let's get the units. So it's 4 megabits. So of course, in this case, we see, well, yeah, A offers 20 gigabits of data. Right, this one is 24. Right, this one offers what, 2 megabits per second of 2 megabits per second of bandwidth. Whereas yeah, this one is what, 4 megabits per second of bandwidth. So of course, yeah, B is going to be better. And yeah, as mentioned, then, well, to go from bytes to bits, right, and vice versa, then of course we'll either just multiply or divide by 8. So we're going from bits to bits to bytes. Yeah, we're going to multiply by 8. From bits to bytes, right, we're going to divide by 8, and then from bytes to bits, okay, we're going to multiply by 8. Alright, so let's look at another example. An MP3 file is 18 megabytes. Right, how many bits is this? Or yeah, how many bits is that? So here then, I mean, well, maybe pause the video, have a go yourself. But what you want to think, well, it's going to be what, 18 and then what, times 1 million. So I mean, let's write 1 million. What we can do, let's just do 10 to the power of 6, right? That's 1 million. Right, then since this is bytes, well, to convert to bits, right, then we need to multiply by 8. And if we do that, if we do that, right, I guess then we're going to get, right, this. So what, 144 million bits. Right, let's look at another one. So an HD MP4 movie averages 4 megabits per second. How many gigabytes would a 2-hour movie use? Okay, so here then we just want to think, well, this is how much it's using per second. Right, then let's multiply it to get, well, how much it's going to use for 2 hours. And I suppose maybe, yeah, like what I'm going to do, I'm probably going to convert this into bits first. And then if we calculate how many bits for 2 hours, right, then once we calculate how many bits for 2 hours, well, then we can just, you know, divide it, right, to get into gigabytes. So to convert how many bits for 2 hours, well, it's going to be, well, 4. Right, then we're going to multiply by, well, yeah, 1 million, right, so 10 to the power of 6. Right, then we want to think, okay, so yeah, this should be how many bits it's using for 1 second. Right, but then since we want a 2-hour movie, what we have to times by 60 to get 1 minute, right, times by 60 again to get 1 hour, right, then times by 2. So this should give us how many bits for the whole 2-hour movie, right, but then we want to convert into gigabytes. So if you remember, to go from bits to bytes, well, first we need to divide by 8. Right, then if we want to convert from, well, I guess, yeah, just sort of bits, right, or bytes, right, yeah, just into giga. So what giga is going to be 1 billion, right, therefore we also need to divide by, what, 10 to the power of 9. Yeah, and to be honest, I mean, you can simplify some of this down. Like, to be honest, well, I mean, here we've got, well, 4 and 2, so yeah, 4 times 2 is just 8. So honestly, like, if we just cancel those, and likewise we can of course then cancel the 8. Likewise, if we have, I guess, what 10 to the power of 6 divided by 10 to the power of 9, what we can just cancel this one, and here, well, that's then going to be 10 to the power of 3. And then I guess what we've just got, well, 60 times 60, right, divided by this. And yeah, I mean, probably you can try that calculation. Although, to be honest, like, in the exam, they wouldn't give you numbers that are this difficult. Now, if you do this, yeah, and I'm probably just going to erase that in a minute, right, that should give us this, right, 3.6 gigabytes, right, for the whole 2-hour movie. Yeah, here it is. Yeah, okay, so again, right, this is going to be the full calculation. And again, as mentioned, of course, well, we can simplify, right, this 1 million divided by 1 billion, right, just to be, you know, divided by 1,000, right, just, yeah, simplifying the powers. Right, and yeah, I guess the thing to note, well, the exam is non-calculator, so as mentioned, right, they're going to use simpler numbers. And yeah, we'll look at some of these questions in another video, right? For example, when we'll look at calculating the image file size, the audio file size, yeah, and also maybe video file size as well. Right, so yeah, let's look at this, right? In maths and science, again, they operate in base 10, however, for computers, well, they operate in base 2. Then, as such, some people are going to use alternate definitions. So we can say, well, 1 ki, or yeah, also Kibi. So I guess, well, let's say, yeah, 1 Kibi byte is going to be, you know, 1024 bytes, right, or 2 to the power of 10. Right, then there's going to be Mebi. So, well, Mebi is going to be 2 to the power of 20. Right, Gibi, right, that's going to be, well, 2 to the power of 30. And Tebi, right, that's 2 to the power of 40. Now, of course, I mean, if you look at these numbers, I mean, yeah, these numbers are kind of horrible. That's why if you just remember, and hopefully you can see what of course goes 2 to the power of 10, right, then 20, then 30, then 40. So of course it's just, yeah, adding 10 each time. And to be honest, I mean, this first one, yeah, I mean, this first one you have to remember, right, yeah, 1024. But of course, I mean, yeah, like these other ones, right, you don't have to remember those. Yeah, just remember, what, 2 to the power of 10, right, 20, 30, 40. Right, so again, yeah, that's just going to be a kind of table showing all of this. And again, right, the full name here, I say Kibi, Mebi, Gibi, and Tebi. And yeah, just the prefixes here as well. Right, so I guess what a problem, right, rather than previously saying 1 Gibi bytes, right, equals, well, this many bytes, because of course, yeah, this is going to be confusing, difficult to understand, and difficult to remember. I mean, yeah, like, I guess, yeah, no, well, I mean, some people can, but yeah, I mean, like, most people are not going to be able to remember that. Then instead we can consider things in terms of the previous group, right, or in terms, yeah, I guess in terms of like 1024. So 1 Kibi byte is going to be, what, 1024 bytes. Right, then we say 1 Mebi byte. Well, this is equal to 1024 Kibi bytes. And right, that's also the same as, what, 1024 squared. Right, then we say, well, 1 Gibi byte is equal to 1024 Mebi, yeah, 1024 Mebi bytes, right, or 1024 cubed. And then you probably can see the pattern, right? 1 Tebi byte is therefore 1024 Gibi bytes, right, or 1024 to the power of 4. And of course, that's just going to go on. Now, of course, I mean, well, yeah, okay, let's see, the reason this works is because, what, 1000, well, let's do that here, right, 1024 is 2 to the power of 10. Right, therefore, if we're saying, well, 1024 squared, that's saying, what, hang on, right, yeah, well, 2 to the power of 10, right, multiplied by 2 to the power of 10. And what, that's just going to equal 2 to the power of 20. And yeah, I mean, if we just go back here, So we saw what, yeah, this is 2 to the power of 20, right? This is 2 to the power of 30. So of course, yeah, that's going to be right why this rule works. All right, now let's try another question. So we see a computer with, well, 16 gigabytes of RAM and another with 16 gigabytes of RAM. Right, how many bits of RAM does each computer have? So I think, well, let's try this one first. I mean, since this one's quite simple. So, right, this one, well, 16 gigabytes, that's going to be, well, 16, right, then giga, so we need to multiply by, what, 1 billion, right, that's 10 to the power of 9. Right, then, well, to go from bytes into bits, okay, what we need to multiply by 8. So, yeah, that's going to be, well, I don't know, yeah, whatever number that's going to be. Right, then, well, 16 gigabytes, so, I mean, it's basically the same. Well, we're going to do 16, but then rather than doing, well, 10 to the power of 9, remember we said, well, Kibi was 2 to the power of 10. Right, Tebi was 2, okay, sorry, right, Kibi is 2 to the power of 10, right, Mebi is 2 to the power of 20, right, Gibi is therefore 2 to the power of 30. And again, we're just going to multiply by 8 because, well, yeah, from bytes into bits. And I guess, I mean, if you do both of those calculations, well, you say, right, yeah, well, this one, okay, so yeah, this one here, right, that's going to equal, right, this horrible number. Whereas if we just look, well, 16 gigabytes, right, well, that's 128 billion. Yeah. Right, then let's look at another example. So you want to download an 800 megabyte file. The server can send at, well, 10 gigabytes per second and receive at 5 megabytes per second. How long will the download take? So again, right, I would say pause the video, have a go at this. Okay, so if you've had a go, like maybe you've got confused because you've seen, well, this, right, 10 gigabytes, or yeah, 10 gigabytes per second. But actually, right, since we can only download at this speed, then, you know, the fact that this one sends faster is actually just completely irrelevant. Like, if we had it where, I don't know, the server can, okay, let's say the server could only send at, like, let's say, well, 2 megabits per second. Well, in this case, of course, well, we can receive faster than the server can send, right? You know, therefore, well, this one is kind of unnecessary. So what I'm saying is, well, I mean, yeah, depending on which one is slower, right, either, I guess, well, either the sending speed, right, yeah, or the receiving speed. I mean, basically all we have to focus on is which one is slower, okay, because, well, yeah, that's going to be the bottleneck. Right, so here then we say our download speed is going to be, well, this one, right, 5 megabytes per second. Therefore, I think probably the easiest way to do this is, I mean, maybe if we just convert, yeah, I think if we, well, of course, if we convert them to the same unit. So probably, right, let's convert this 800 megabytes, right, into 800, okay, sorry, yeah, into mebibytes. Then, of course, we can just, yeah, you know, directly divide them. Right, so we're 800 mebibytes. If we just do that, like, I mean, you can do it without converting to bits, but for me, I actually like to convert to bits first, and yeah, then just convert from bits, you know, back into the second unit. So to convert to bits, well, again, well, that's going to be 10 to the power of 6. Right, then what to, and I suppose, I mean, yeah, here actually we don't need to convert into bits, I mean, since they're both in bytes. So yeah, let's just leave that. Right, then what we want to do, well, so right, this is going to give us how many bytes. Now, to go from bytes right into, well, mebibytes, we just want to do what is going to be, well, 1024, right, squared. Yeah, or alternatively, well, of course, we can say, what, 2 to the power of 20. Now, of course, I mean, yeah, this is going to be too difficult to do, you know, sort of in your head, right? But yeah, of course, you know, with a calculator, right, you can do this. Right, then what you're going to do, so, okay, that's going to be our answer. And that's going to be what the total file size. Then I guess if we just do the whole thing, what, divided by 5, because of course, I mean, what, well, this thing is going to be in mebibytes, right, the file size. Yeah, the download speed is also mebibytes, right? Therefore, we can download them. Okay, we can divide them directly. And I mean, if you do that, well, let's just see what the answer is going to be. Yeah, if you do that, right, then you should get an answer of, well, 2 minutes 33 seconds. And like I would say with these kind of questions, I mean, when you get an answer, you know, check if it's reasonable, because I mean, well, of course, you know, it's quite easy to make a mistake, right? Maybe you do 10 to the power of 9 or something instead, or, you know, you do, like, I don't know, 2 to the power of 30 or 2 to the power of 10. Now, if you get something where it says, I don't know, you know, like 10,000 minutes, so you can just estimate this quickly by doing, what, 800 divided by 5, and I mean, that's going to be, what, approximately, I don't know, yeah, 100 and something. Yeah, you know, I don't know the exact thing, or I've not calculated it. And if you think, well, I mean, that's going to be about, what, 2.5 minutes, because, well, 2.5 minutes, what, 2 minutes is going to be 120 seconds, right, 2.5 minutes, well, that's going to be, what, like 150 seconds, so yeah, 2 minutes 53, right, well, 153 seconds. So again, you know, these, right, I mean, you can probably kind of check your answer, right, just by estimating. And again, like, in the exam, they're also going to use simpler numbers. So if you get some horrible, like, fraction, or some horrible decimal, yeah, then of course, right, that's not going to be correct, right? You're always going to get, well, either a whole number, possibly you might get like a 0.5, right? So I don't know, like an 8.5. Yeah, maybe they might give you a quarter, but if you start getting, I don't know, you know, I'm gonna say, like, yeah, I guess 8.12, right? Well, yeah, that's definitely going to be wrong, right? They're not going to give you something that difficult. Alright, so just a task then, right, what you can do, you can find the storage size of, let's say, well, your SSD, right, solid state drive, yeah, your hard drive, right, maybe the cache inside the processor, right, maybe, well, how much storage is remaining, how much storage you've already used, and then, I mean, just practice doing various conversions. So, for example, let's say if you have, I don't know, maybe 752 GB worth of storage remaining, right, on either your hard drive or your SSD, then, I mean, well, how many, let's say, how many Tebi bytes is that going to be, how many bits is that going to be, yeah, how many megabytes is that going to be? Yeah, of course, just practice converting them. And then, yeah, I guess online there's going to be many websites. I mean, this one here, you know, seems okay. Yeah, this is going to show all of them in one go. It's going to show bits, bytes, you know, well, obviously, yeah, mega, Mebi, right, Kibi, right, it's going to show all of them. Yeah, so I think, yeah, guys, so again, I mean, hopefully this video is useful. And if you've got any questions, well, just ask in the comments. Right, then see you in the next video.